Let's do another example of limit comparison test. Um, let's look at this summation, and as usual we want to just get a rough sense at first of what's dominating when k is large. And it's important to note that when k is large, 4 to the k, when the large number is in the exponent, it's going to be a lot bigger than k to the fourth. And similarly, 3 to the k is going to be a lot bigger than k cubed. Exponents always dominate when they get big. And so it's more or less like 4 to the k over 3 to the k. And so we're going to want to compare it to that because, and this is one reason I want to do this example, we know what that kind of example does. The geometric series, that's as well as along with the p-series, that's our big comparison series. And that is that the sum of r to the k, and of course it could be 0, 1, 2, whatever, doesn't really matter too much. This converges exactly when that r is a small number. The absolute value of r is strictly less than 1 and diverges otherwise. Now, we're talking right now, until the next section, we're talking about series of positive terms, so we would just be looking at positive r's, and it's just whether it's smaller than 1 or greater than or equal to 1. So this is absolutely huge, probably the most important series of all, and it's a great comparison. And this is something that when k is really large, it's going to be look very much like a geometric series, and the geometric series we're going to compare it to is 4/3. So our b sub k is 4/3 to the k, and therefore we're going to expect, and we're going to try to show, that our complicated series diverges because of what we know about geometric series, that diverges. Okay, so we just want to take the limit as k goes to infinity of our series divided by 4/3 to the k. Well, in other words, times 3. Actually, you know what? I'm going to write it as, well, we could write it as times 3/4, 3 to the k over 4 to the k. But you know what? It's going to be nice. When we have limits, fractions, especially limits at infinity, we want to tame the top and tame the bottom. This is an infinity over infinity limit here, and we'd like to see if we can tame that, and this is going to actually let us do that very nicely if we write it as 1/4 to the k over 1/3 to the k. So we're dividing by 4 to the k and then dividing by 1 over 3 to the k, and so that's one way to do that. And so that's going to be, okay, now that we know what that geometric series does, we don't want to use that space. And that's going to be limit k goes to infinity of 1 minus k to the 4th over 4 to the k over 1 plus k cubed over 3 to the k. Okay, and now, depending on how paranoid you want to be, you could quote a general result about exponential expressions beating polynomial expressions, in which case this goes to 0, and this also goes to 0, and then this is 1. That's certainly finite, non-zero, and that's saying that we found a very accurate comparison that when k is large, these numbers are quite close to 4/3 to the k, and therefore this series diverges. If you wanted to be a little bit more careful, as you might have to be like on an AP test or something, about why these go to 0, you could do just a separate limit. You can promote that to be a real variable, like x to the 4th over 4 to the k, and do L'Hopital's. You'd have to do it multiple times. But when you do L'Hopital's, this spits out factors of ln4, but otherwise stays the same. And this goes x to the 4th, x cubed, x squared, x, it dies. Really, what you should have is a little general lemma saying exponentials always be polynomials because and you can always refer to L'Hopital. So I'm going to not do the details of that. So these guys go to 0, this whole thing goes to 1, and that confirms our intuition that in the large, those things don't matter, and it's 4 to the k over 3 to the k. So notice that this would have been a little bit of a pain with the straight comparison test because the numerator is, strictly speaking, less than 4 to the k, and the denominator is bigger than 3 to the k. So it appears to be slightly better. And when k is medium, this actually is a pretty big knockoff here, and this is a pretty big increase. It's only when k gets really, really large that starts to not matter. But of course, that's what we care about. So that's why the limit comparison test in this kind of example is superior.